Load balancing with 480 volts line-to-line heaters can be achieved using a Delta-Wye transformer connection. Firstly, connect 3 heaters in Delta. Wire the first 3 heaters in a Delta configuration as follows. Connect the line wire from phase A to the terminal of heat. 1. Connect the line wire from phase B to the B terminal of heat. 2. Connect the line wire from phase C to the C terminal of heat. 3. Connect the neutral wire from the power source to the common connection point of the heaters. Secondly, connect the 4th heater in Y. Install a single-phase 480 volts to 277 volts transformer with a capacity of at least 2.5 kilowatts. Wire the secondary 277 volts terminals of the transformer in a Y configuration. Connect the horn terminal of the transformer to the terminal of heater 4. Connect the H3 terminal of the transformer to the B terminal of heater 4. Connect the neutral wire from the power source to the neutral terminal of the transformer. Now let's analyze the load balancing. The 3 heaters connected in Delta will draw the same load, resulting in equal currents on phases A, B, and C. The 4th heater connected in Y through the transformer will draw its load from a combination of phases A and B. The neutral wire will carry the difference in current between the Delta and Y loads. Advantages of the Delta-Wye connection are that it maintains load balance on the transformer and power system. It allows for the use of 480 volts line-to-line heaters even when only a single-phase transformer is available. It reduces voltage drop on the heater loads. Note the transformer used for the Y connection must have a capacity of at least 2.5 kilowatts to handle the load of heater 4. The neutral wire must be appropriately sized to carry the difference in current between the Delta and Y loads. Considering the initial setup with a 10 kV single-phase transformer on phases A and B, and the requirement for 4 2.5 kW line-to-line 480 volts heaters, the challenge lies in effectively balancing the load across the available phases. The suggestion of using a Delta configuration for 3 heaters is a sound approach, as it distributes the load evenly across phases A, B, and C. However, the question remains on how to integrate the 4th heater without disrupting this balance. The Delta-Wye configuration addresses this issue by utilizing a step-down transformer to convert the 480 volts to 277 volts for the 4th heater, which is then connected in a Y configuration. This setup ensures that the load is distributed in a manner that minimizes imbalance in the single-phase transformer. To elaborate further, let's consider the implications of each connection type. In a Delta connection, each heater is connected between 2 phases, drawing current from both. This configuration is ideal for 3-phase systems as it naturally balances the load, assuming the heaters have similar power ratings. However, in a single-phase system, directly connecting all 4 heaters in a Delta configuration is not feasible, as it would overload the available phases and lead to significant imbalances. On the other hand, a Y connection involves connecting each heater between a phase and a neutral point. This configuration is commonly used in both 3-phase and single-phase systems. In the context of the Delta-Wye configuration, the 4th heater is connected in a Y configuration via a step-down transformer. This arrangement allows it to draw power from a combination of phases A and B, effectively spreading the load and reducing the burden on any single phase. The transformer steps down the voltage from 480 volts to 277 volts, which is suitable for the Y-connected heater. The neutral wire plays a crucial role in carrying any unbalanced current between the Delta and Y loads. It ensures that the voltage remains stable and that the heaters receive the appropriate voltage levels. Proper sizing of the neutral wire is essential to prevent overheating and voltage drops. The selection of the transformer is also critical. It must have a capacity of at least 2.5 kilowatts to handle the load of the 4th heater. A higher capacity transformer may be necessary if there are any additional loads on the system. Furthermore, the transformer should be chosen based on its efficiency and voltage regulation characteristics. A high-efficiency transformer will minimize energy losses, while good voltage regulation will ensure that the heater receives a stable voltage even under varying load conditions. In terms of wiring, it is important to follow all applicable electrical codes and standards. This includes using the correct wire sizes, grounding techniques, and overcurrent protection devices. Proper wiring practices will ensure the safety and reliability of the system. In summary, the Delta-Wye configuration offers a practical solution for balancing the load of four 480 volts heaters on a single-phase transformer. By connecting three heaters in a Delta configuration and the fourth heater in a Y configuration via a step-down transformer, the load is distributed in a manner that minimizes imbalance and ensures the efficient operation of the system. Remember to select the appropriate transformer size, wire sizes, and overcurrent protection devices to ensure the safety and reliability of the installation. Additionally, consulting with a qualified electrician is recommended to ensure that the installation meets all applicable codes and standards. Let's delve a bit deeper into the specifics of selecting the right components and performing the calculations necessary for a successful implementation of this Delta-Wye configuration. Choosing the correct transformer for stepping down the voltage to supply the fourth heater is crucial. The transformer's kilovolt ampere rating needs to be sufficient to handle the load, and selecting an appropriately sized transformer prevents overheating, voltage drops, and potential damage. To calculate the minimum kilovolt ampere rating required, we need to consider the power consumption of the fourth heater, which is 2.5 kilowatts. Assuming a power factor of 1, the kilovolt ampere rating is simply equal to the kilowatt rating, so we need at least a 2.5 kilovolt ampere transformer. However, it's always a good practice to add a safety margin of around 20% to account for potential future load increases or variations. This would bring the recommended transformer size to approximately 3 kilovolt ampere. Selecting a transformer with a slightly higher rating will also ensure that it operates more efficiently and reliably. Next, we need to determine the appropriate wire sizes for the connections to the heaters and the transformer. The wire size is determined by the amount of current it needs to carry, as well as the allowable voltage drop. The National Electrical Code, or NEC, provides tables and guidelines for selecting the correct wire sizes based on the ampacity of the wire and the type of insulation. To calculate the current drawn by each heater, we can use the formula current equals power divided by voltage. For the 480 volts heaters connected in Delta, the current drawn by each heater is 2500 watts divided by 480 volts, which equals approximately 5.21 amps. For the 277 volts heater connected in Y, the current drawn is 2500 watts divided by 277 volts, which equals approximately 9.3 amps. Based on these current values, we can consult the NEC tables to determine the appropriate wire sizes. For example, using NEC table 310.15b16 for typical copper conductors with THHN insulation, a 14 American wire gauge wire is typically rated for 15 amps, which would be sufficient for the 5.21 amps drawn by the Delta connected heaters. However, it's important to consider factors such as ambient temperature, conductor bundling, and conduit fill, which may require using a larger wire size to maintain the ampacity of the conductors. For the 9.3 amps drawn by the Y-connected heater, a 12 American wire gauge wire is typically rated for 20 amps, which would be sufficient. Again, it's important to consider any directing factors that may apply. In addition to selecting the appropriate wire sizes, it's also crucial to choose the correct overcurrent protection devices, such as circuit breakers or fuses. These devices protect the wiring and equipment from overloads and short circuits. The size of the overcurrent protection device should be based on the ampacity of the conductors it is protecting, as well as the rating of the equipment. For the 480 volts heaters connected in Delta, a 15 amp circuit breaker or fuse would be appropriate for protecting the 14 American wire gauge wires. For the 277 volts heater connected in Y, a 20 amp circuit breaker or fuse would be appropriate for protecting the 12 American wire gauge wires. It's important to note that these are just examples, and the actual wire sizes and overcurrent protection devices may vary depending on the specific installation conditions and local electrical codes. Consulting with a qualified electrician is always recommended to ensure that the installation meets all applicable requirements. Furthermore, proper grounding is essential for the safety of the electrical system. Grounding provides a low impedance path for fault currents to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. The grounding system should be installed in accordance with the NEC and local electrical codes. This includes grounding the transformer enclosure, the heater enclosures, and any metallic conduits or enclosures. In summary, implementing a Delta-Wye configuration for balancing the load of four 480 volts heaters on a single-phase transformer requires careful consideration of component selection, wiring practices, and overcurrent protection. By choosing the correct transformer size, wire sizes, and overcurrent protection devices, and by following all applicable electrical codes and standards, you can ensure the safe and reliable operation of the system. Always consult with a qualified electrician to ensure that the installation meets all applicable requirements and to address any specific concerns or questions. Now, let's consider the practical aspects of installing and connecting the heaters in a Delta-Wye configuration, along with some troubleshooting tips for common issues. Before starting any electrical work, it's essential to disconnect the power supply to the circuit. This can be done by turning off the circuit breaker or removing the fuse that supplies power to the transformer and the heaters. Always verify that the power is off using a reliable voltage tester before touching any wires or components. Once the power is disconnected, you can begin installing the heaters. The Delta-connected heaters should be wired in a triangular configuration, with each heater connected between two phases. The Y-connected heater should be connected between a phase and the neutral point, using the step-down transformer to provide the appropriate voltage. When connecting the wires to the heaters, be sure to use properly sized wire connectors and to tighten the connections securely. Loose connections can cause overheating, voltage drops, and potential fire hazards. After the heaters are installed and wired, you can connect the transformer. The primary side of the transformer should be connected to the 480 volt single-phase power supply, while the secondary side should be connected to the Y-connected heater. Be sure to follow the transformer manufacturer's instructions for proper wiring and grounding. Once all the connections are made, double-check everything to ensure that it is correct and secure. Then, you can restore the power supply to the circuit and test the heaters. Use a multimeter to verify that the voltage at each heater is within the acceptable range. Also, check the current drawn by each heater to ensure that it is within the expected limits. If you encounter any issues, such as a heater not working or drawing excessive current, there are several troubleshooting steps you can take. Firstly, check the circuit breaker or fuse to make sure it has not tripped. If it has, reset it and try again. If the circuit breaker trips repeatedly, there may be a short circuit or an overload in the circuit. Secondly, check the wiring connections to make sure they are tight and secure. Loose connections can cause a variety of problems, including overheating, voltage drops, and intermittent operation. Thirdly, test the heater elements to make sure they are not burned out or damaged. Use a multimeter to measure the resistance of each heater element. A burned-out heater element will typically have an infinite resistance. Fourthly, check the transformer to make sure it is working properly. Use a multimeter to measure the voltage on both the primary and secondary sides of the transformer. If the transformer is not providing the correct voltage, it may be faulty and need to be replaced. Fifthly, check the grounding system to make sure it is properly installed and connected. A faulty grounding system can cause a variety of problems, including electrical shock hazards and equipment damage. In addition to these troubleshooting tips, it's also important to perform regular maintenance on the heaters and the transformer. This includes cleaning the heaters to remove any dust or debris, inspecting the wiring connections for any signs of damage or corrosion, and testing the transformer to ensure that it is operating within its specifications. By following these practical tips and performing regular maintenance, you can ensure the safe and reliable operation of the heaters and the transformer. Always consult with a qualified electrician to address any specific concerns or questions and to ensure that the installation meets all applicable requirements. Now let's address some advanced considerations and potential modifications to the Delta-Wye configuration for balancing heater loads, particularly in scenarios with specific constraints or requirements. One advanced consideration is the use of autotransformers instead of traditional isolation transformers. Autotransformers are a type of transformer that uses a single winding for both the primary and secondary circuits. This design can be more efficient and cost-effective than traditional isolation transformers, but it also has some drawbacks. One drawback is that autotransformers do not provide electrical isolation between the primary and secondary circuits. This means that any voltage fluctuations or transients on the primary side can be transferred to the secondary side, which could potentially damage the Y-connected heater. Another drawback is that autotransformers may not be suitable for all applications, particularly those where safety is a major concern. However, in certain situations, autotransformers can be a viable alternative to traditional isolation transformers. Another advanced consideration is the use of variable autotransformers, also known as variacs. Variacs allow you to adjust the voltage output of the transformer, which can be useful for fine-tuning the heat output of the Y-connected heater. However, variacs are typically more expensive than fixed voltage transformers, and they may not be suitable for all applications. A potential modification to the Delta-Wye configuration is the use of a three-phase transformer instead of a single-phase transformer. A three-phase transformer can provide a more balanced load on the power system, which can be beneficial in certain situations. However, three-phase transformers are typically more expensive than single-phase transformers, and they may require a more complex wiring installation. Another potential modification is the use of solid-state relays, or SSRs, to control the heaters. SSR are electronic switches that can be used to turn the heaters on and off without the use of mechanical contacts. This can improve the reliability and lifespan of the heaters, as well as reduce the amount of electrical noise generated by the switching process. However, SSR are typically more expensive than traditional mechanical relays, and they may require a more complex control circuit. When considering these advanced considerations and potential modifications, it's important to carefully evaluate the specific requirements of the application and to weigh the benefits and drawbacks of each option. Consulting with a qualified electrical engineer is always recommended to ensure that the chosen configuration is safe, reliable, and cost-effective. Furthermore, it's important to consider the impact of the heater loads on the overall power system. Large heater loads can cause voltage drops and harmonic distortion, which can affect the performance of other equipment connected to the power system. It may be necessary to install power factor correction equipment or harmonic filters to mitigate these effects. In addition to these advanced considerations and potential modifications, it's also important to stay up to date on the latest electrical codes and standards. The NEC and other electrical codes are constantly evolving, and it's important to ensure that your installation meets all applicable requirements. By staying informed and consulting with qualified professionals, you can ensure that your heater load balancing system is safe, reliable, and efficient. Let's explore some strategies for optimizing the energy efficiency of the heater system while maintaining effective load balancing. Energy efficiency is a crucial consideration in any electrical system, and heater systems are no exception. Optimizing the energy efficiency of the heater system can not only reduce energy costs but also minimize the environmental impact. One strategy for optimizing energy efficiency is to use programmable thermostats. Programmable thermostats allow you to set different temperature schedules for different times of the day or week. This can help you avoid heating unoccupied spaces or heating spaces to unnecessarily high temperatures. Another strategy is to use occupancy sensors. Occupancy sensors can detect when a space is occupied and automatically turn on or off the heaters accordingly. This can be particularly useful in spaces that are not always occupied, such as offices or storage rooms. Another strategy is to use variable speed heaters. Variable speed heaters allow you to adjust the heat output of the heater to match the heating demand. This can help you avoid overheating spaces or wasting energy by running the heaters at full capacity when it is not necessary. In addition to these strategies, it's also important to ensure that the building is properly insulated. Proper insulation can help reduce heat loss, which can significantly reduce the amount of energy required to heat the space. It's also important to seal any air leaks in the building envelope. Air leaks can allow warm air to escape, which can also increase energy consumption. Another strategy is to use radiant heaters. Radiant heaters heat objects directly rather than heating the air. This can be more efficient than traditional convection heaters, as it avoids heating the air, which can then be lost through air leaks. In addition to these strategies, it's also important to perform regular maintenance on the heater system. This includes cleaning the heaters to remove any dust or debris, inspecting the wiring connections for any signs of damage or corrosion, and testing the thermostats and sensors to ensure that they are working properly. Another strategy is to consider the use of renewable energy sources, such as solar thermal or geothermal energy, to supplement the heater system. These renewable energy sources can provide a sustainable and cost-effective way to heat the space. When implementing these energy efficiency strategies, it's important to consider the impact on load balancing. Some energy efficiency measures, such as using programmable thermostats or occupancy sensors, can affect the load on the power system. It's important to monitor the load on the power system and adjust the energy efficiency measures accordingly to maintain effective load balancing. By implementing these energy efficiency strategies and monitoring the load on the power system, you can optimize the energy efficiency of the heater system while maintaining effective load balancing. Always consult with a qualified energy efficiency professional to ensure that the chosen strategies are appropriate for the specific application and to address any specific concerns or questions.